We're going to look at some weird stuff in this video, but we're going to start off by something very simple. Here I have the reaction of a carboxylate with methyl iodide. Use your knowledge from 321 to predict the product of this reaction. What's going to happen? Well, here's some choices. We could have the methyl show up on the oxygen. We could have the methyl show up on the carbon of the carbonyl, form this tetrahedral intermediate. We could have the methyl show up on the carbonyl oxygen. Or we could have the iodide show up somehow magically. Well, what's going to happen? Well, you took 321. You know what's going to happen. We're going to do an SN2 reaction. The carboxylate is going to attack the methyl, kicking out the iodide being a pretty good leaving group. So this is a Chem 321 way of making esters. Now, it turns out, though, that it's not very general. The reason it's not very general is the problem with the carboxylate. So are carboxylate excellent nucleophiles? Are they mediocre nucleophiles? Actually, they're horrible nucleophiles. The choice is C. They're terrible nucleophiles. They only react with methyl primary benzyl allylic substrates. The most reactive substrates you can have will react with a carboxylate. And they don't necessarily do it all that cleanly. It's not a great way of making an ester, and it's certainly not general. Plus, often, of course, you don't have things like the iodides of your substrate. Much more common are alcohols, and you'd rather not have to make a halide if you don't have to. So this is not a great way to do it. How could you make a reaction better? Well, iodide's a great leaving group, but could we come up with a better leaving group? Could we find an even better way of making at least methyl esters? And it turns out, well, let's look at different leaving groups. Iodide is great. Fluoride, is that better than iodide? Actually, if you remember your rules from last semester, fluoride is a terrible nucleophile, or a terrible leaving group. It forms too strong a bond. So fluoride is not a good leaving group. Triflate's a pretty good leaving group because you activate alcohols by making triflates. But something even better than triflate is N2. What could be better than N2? It's dinitrogen, very, very stable molecule. But doesn't it sound a little bit crazy? How could we make N2, put N2 into that compound right there? Well, what we need this. Does it look good? Does it look fine? Or is this, am I trying to pull one on you? Well, this is real. This is a real species. This cation looks a bit strange, but you can generate it. How does that work? Well, and once you've got it, the reaction works great. So how do we get that molecule? Well, we start with an even weirder looking species, this neutral molecule. This neutral molecule, look at this, a carbon-nitrogen double bond, then another double bond. Of course, you need these charges in here to balance out the electrons. This is called diazomethane, and it's a real molecule. And we'll talk in a second how we make it. So this will react with carboxylic acids really, really well. And it's very specific. And there's no general way of making esters, because the diazomethane is such a specific molecule. But the way it works is you simply protonate that double bond, and you make that cation, which we showed on the previous slide, that one that looks so weird. And this is indeed, just look at this. This thing has got the world's best leaving group on it. That carboxylate will attack the methyl and kick out that N2 just like a shot. It's gone, and you formed N2 thermodynamically. This is absolutely wonderful. You release that N2 as a gaseous molecule, so it's so incredibly stable. So this is a great reaction if you have the diazomethane. In fact, it turns out getting the diazomethane is the problem, because there's zero problem with the reaction once you have it. But how do we get the diazomethane? Well, I'm going to show you. I don't expect you to remember it, but I'm going to show you. The way it's made is through a series of reactions. But first we have to do a setup for our proper reagent. And the reagent itself is made this way. We start with another compound, which is called methyl urea, and react it with nitrous acid. Okay? Nitrous acid itself comes from sodium nitrite and HCl. So the nitrogen of one of the nitrogens of the methyl urea attacks the nitrogen of the nitrous acid. We do some proton shuffling around here. We do a little bit more proton shuffling around to set up, or we kick out the water. This sets up a water for leaving, bring in those electrons, kick out the water, and we get this molecule here. And this one you can actually buy. So this is where the real reaction for generating the diazomethane begins. You start with this guy, you throw in some hydroxide, it attacks the carbonyl, forms a tetrahedral intermediate. We kick out this piece on the left. Okay, we're just going to move around protons here, and because we're in base, this gives you this guy. We'll just form a different resonance structure. Here, form this resonance structure, and from this you can see that we're all ready to kick out a water molecule. We can kick out that water molecule by bringing a lone pair of that nitrogen down to form a double bond, kick out the hydroxide, and there's our diazomethane. So this is actually, chemistry works really well. It's just that there's a number of problems in doing this. The first problem is that this compound is extraordinarily dangerous. It's very carcinogenic, it's very reactive, and it's nasty stuff which you don't want to deal with if possible. These days, there's a more modern alternative around, which here's an example of this. It's from a sulfonic acid, but this itself is still dangerous, and the diazomethane itself is another wrinkle. Is we know that the nitrogen really wants to get out of this molecule. What that means is that this molecule is also very explosive, and almost anything will set it off in terms of the explosion. And one thing that you have to avoid is friction. And so people have special glassware which has no ground glass joints, nothing can cause a scratch or a little bit of friction or anything to do this chemistry. And it's very, very dangerous, and only a very experienced organic chemist with lots of training is going to use this stuff. But people do use it, and the reason they use it is because the diazomethane is so good at making methyl esters. You can have a really complex molecule, all kinds of functionality in it, and if it has a carboxylic acid hanging off someplace, you can convert that to a methyl ester using diazomethane. Very specific and very nice reaction. But having said all that, you may now forget this slide. It's too complicated. I don't want you to, don't fill up your brain with this slide. But it's nice to know that such weird things actually exist, and that some people are brave enough to actually use it. But on this subject, let's go back to the subject of SN2 reactions. What about the reverse? Can you take these methyl esters apart using SN2 chemistry? Is this a good reaction? Doesn't look too bad. We know hydroxide is a good nucleophile, and acetate's a reasonably good leaving group. So it doesn't look too bad. And it turns out, well, the reaction does work, but the mechanism is wrong. This is not the way it works. Because the hydroxide can do something better. Instead of attacking the methyl, it can attack the carbon and the carbonyl. Actually, remember, there's a partial positive charge there. So the hydroxide attacks the carbon or the carbonyl instead. It forms this nice tetrahedral intermediate, and now we kick out the methoxide, we form a carboxylic acid, but we're in base, so that immediately goes to the carboxylate. So this is the way the reaction works. It's not an SN2 reaction. It's a common mistake that people make, but this other route works so much better. Now, what if we don't have such a great nucleophile? What about this one? What if we take a chloride and attack the methyl? Well, in this case, it's actually not so bad. If we do this in a polar aprotic solvent, you may remember from 321 that polar aprotic solvent makes the chloride a better nucleophile. And the alternative of the chloride attacking the carbonyl gives you a tetrahedral intermediate, okay, but the problem with that is that the chloride is a better leaving group than the methoxide. So if the chloride attacks the carbon of the carbonyl, it'll just kick itself back out again. It won't be a productive reaction. So adding the chloride to the carbonyl in this case doesn't lead anywhere, whereas attacking the methyl directly does by kicking out the acetate. Now this works for methyl esters, and you can probably get away with it with something simple like an ethyl group on there. But this generally is not great chemistry. And if we want to make alkoxides from our esters, generally what one does is use base hydrolysis. And we'll talk about that more on the following video.